Rahim. Welcome to LabVIEW Core 1 training part 4. Before coming to discuss this exercise 5.1 of lesson 5, I would like to discuss an additional topic that is not particularly connected to lesson 5, but it is important information that I want to share, that there are some other data types as well. One data type is dynamic data type. Basically, dynamic data type stores the information generated or acquired by an express VI. Express VIs offer dynamic data type. Let me demonstrate you in LabVIEW. Go to Express VI folder and pick up a simulate signal Express VI. Let the settings be as it is. Click OK and then click create a graph indicator to see the output. Alright. Now please note, waveform data type is not just an array of numbers, but it is a special kind of cluster that contains additional timing information as well. When you run it, you see that it has additional timing information as well. It includes timing information that, like, this signal is from 0 to 0.1 seconds. It also includes name of x-axis. You see, name has automatically been allotted. And it includes name of axis, time, and it also includes name of plot. This is a benefit of dynamic data type. So this is a dynamic data type. Alright. Make duplicate of this express VI and configure it to generate a different wave. Maybe a triangle. Alright. And then connect the two outputs together. Connecting together without operations such as build array or build cluster or something else like that will lead to broken VI. However, the dynamic data type has built-in intelligence. Like, you notice that it has a built-in intelligence, like such that it automatically adds a merge signal function. So this is also the beauty of express signal VI, that it has built-in intelligence such that it automatically adds merge function so that our VI is not broken. Run this program. Now you see a sine wave and a triangle wave together. Expand this legend to see both sine and triangle. Now modify the second express VI so that it has now number of samples 300. So now it has more data points than before. Click OK, hit the run button, make it 0.3. Check once again. Please make it 300. 300. Now data points are more than 100 than before. Now click OK and run it and move it to 0.3. Now you see that the sine wave has only 100 samples, so it ends at 0.1 seconds. But triangle waveform has increased data points, so it has increased data points and therefore it goes up to zero point 0.3 seconds, whereas sine only goes up to zero point 0.1 seconds. Alright. The data coming from Express VI can be given to some other data types as well. In this case, please pick up a array of numeric control and connects, make it change to indicator and connect it. You notice that it has built-in intelligence such that an additional functionality is performed, which is called convert from dynamic data. Now it basically converts from dynamic data to array. This is the function. Click it. You see only two values. You see only two values. Now what if you want to see the complete array? Double click it and then you see this is Express VI that configure convert from dynamic data type to other data types. You should select 1D array of scalars single channel. Click OK. Create a control here for which channel you want to select. And now hit the run button. Channel 0 is sine wave. Go to visible atom. Now you see this is a sine wave data. This is basically a sine wave data. Enable the vertical scroll bar and there are 100 data points in this sine wave. These are the 100 data points. So this is the data coming from a sine wave and you can see in the array. And it has also come with the built-in intelligence of Express VI that dynamic data type is automatically converted into array. Alright, if you want to see triangle waveform, you can see triangle waveform. Now it should have more data points, 300 data points. As compared to sine wave, it should have 300 data points. Alright. Okay. You can also try some other Express VIs as well from this signal manipulation subpalette, like try this select signal. You see these functions are available from convert to dynamic data type, like you can convert to dynamic data type or you can convert from dynamic data type. Both Express VIs are available over here. Alright, merge signal is there, select signal is there, you can use select signal, Express VI. Alright, press OK, select the signal here, and when you double click it now, let us say you want to select signal 1, and then copy this sine wave here, connect it here, and run it. So you see signal 1 is selected, triangle signal is selected, and you can see the triangle signal here. So we discussed about dynamic data type now. which is basically stores the information generated or acquired by an express VI. The other data type we are interested to discuss is waveform data type. This waveform data type carries the data, start time, and also DT of a waveform. We will discuss this a little later on. So let us move to now exercise 5.1. Let us start this exercise 5.1 and refer to participant guide. Alright. So manipulating array, exercise 5.1. Manipulation arrays using various LabVIEW functions. Description: you are given a VI asked to enhance it for variety of purposes. The front panel of this VI is built. You complete the block diagram to practice several different techniques to manipulate arrays. Implementation: go to this, open this LabVIEW project, manipulating array, enter exercise LabVIEW code 1, manipulating arrays. Like code 1, exercise code 1, and refer to manipulating arrays. So this is the manipulating arrays. And from here, you should open this LabVIEW project, manipulating arrays. I have already opened it. Okay. Then open this VI, array manipulation. This is its front panel. This is already built for you. Now open the block diagram and complete each of the cases that correspond on the tapes on the different front panel as shown in figure 5.2 through 5.8. So first you create this part of the code. You have to use concatenate channel. Go to the block diagram and do these settings. Control E to open block diagram, maximize it. You see this is a sine waveform function. You can get it by searching sine waveform. This is basically a sine waveform. Alright, and this is basically a square waveform. You can search a square waveform like this way. This is a square waveform. This gives you a sine waveform, this gives you a square waveform. Alright. Okay. Now in order to see the output, this is basically a waveform graph, and this is basically array. Now take build array function and resize it to 2 nodes. Connect these 2 inputs. Okay. And now if you try to connect this here and here, you get broken arrow. Why do you get a broken arrow? Here we need to have the discussion on this reason. Basically, now you are getting 1D array of the sine waveform and you are getting another 1D array from this sine waveform. And if this concatenate input is not selected, then as you know that we have previously studied that in result you will get a higher dimension array, in this case a 2D array. So certainly here this numeric indicator is basically array of floating point dBl, but it is a 1D array. How can you connect a 1D array numeric indicator to 2D array? It is not possible. Therefore, it is showing broken VI. You can see the data on the waveform graph. This is possible to see 2D array on this waveform graph, but how can you see a 2D array on numeric indicator of 1D array? This is not possible. Therefore, when you connect it, you get this broken VI. In order to overcome this problem, you can right-click this build array and select this concatenate input. Now when you select this concatenate input, then it will link together these two both 1D arrays in series, and in result you will also get 1D array. Let me turn on here control help and show you this. You see this is a 1D array. It is clearly written this is a 1D array. But when it concatenate input was not selected, then in that case it is a 2D array. Resulting from here is a 2D array. You can see it, 2D array. Alright. So therefore we concatenate input to basically see the sine waveform and square waveform in a 1D array. Alright. Simply when concatenate input is activated, is selected, then you get in result 1D array. Now you should switch to the front panel and then you should run this VI in order to see the results. Notice that the sine wave is concatenated with a square wave. Sine wave and square wave are linked together in a 1D array. As the data from sine wave finishes, then a square wave starts. So this is the function of build array when concatenate input is basically selected or activated. Now let us try to see the result on waveform graph without without this concatenate input. So I remove it and I see this 2D array without this concatenate input activated on this waveform graph. Now I expect to see a higher dimensional array, and you see these are not concatenated, but rather I am getting a 2D array with two different data types. One is the sine waveform, the other is the square waveform. So I hope now the concept is clear. All right. Okay. What is this function? Let me also tell you about this function get waveform component. You can press control space and get this waveform component. Sorry. Get waveform component. Now you can actually this sine waveform produces waveform data type. The data type that this function results in is waveform data type, and waveform data type is already discussed consists of three things: dt, initial time, and waveform component. In order to extract only waveform component, you see we have selected this waveform component y only, and we have given to it, and only the waveform component is extracted here. We are not interested with the time component, therefore we have extracted the waveform from this waveform data type, therefore this get waveform component is used. And here, this is waveform data type, and this will consist of both initial time, dt, and waveform as well. So I hope you are clear about now that this is a waveform data type. Like previously we discussed dynamic data type. Now this is waveform data type, and waveform data type carries the data start time and dt of waveform. So in order to extract only waveform component, we have used this component, this function get waveform component. Alright, and then a build array function is used. Okay. Now switch the block diagram and select 8 subtract channels. Select 8 subtract channel case, and now you should perform addition and subtraction operation on these both signals. For that, I take a case structure. This is conditional terminal of the case structure, and this is a Boolean data type. And when this Boolean switch is connected with this conditional terminal, you will get only two conditions, either true or false. In true condition, I want that there should happen subtraction of these both signals. So I take a subtract function, and I want to subtract basically sine wave from the square wave when this subtract button is activated, and I want to see the result on waveform graph as well as on this 1D array. Alright, and when this subtract button is false, in that case I want the addition to be performed. Alright, so you have placed a case structure and place a subtract function in the true case so that vi subtracts the elements of the array when the subtract button on the front panel is pressed. When the value of the subtract boolean control is false, the array elements are added as per this coding. Alright. Now please note that the case structure, the case demonstrates polymorphic functionality by adding and subtracting elements of the array. So it is itself case is itself a polymorphic function. It has polymorphism capacity. Now switch to the front panel and see the results in this add subtract channel type. Run the VI. Now you see these two signals are added when subtract is false, and when subtract is true, sine wave is subtracted from the square wave. So you can subtract or add the sine wave with the square wave. Both possibilities are there with the help of case structure. We will discuss in detail case structure in our coming lecture. For time being, for now, you should understand that this case structure, as it is connected with the conditional terminal of the boolean, so it gives you two possibilities. If this is false, like here, if this at this time this is false, so sine wave is added with the square wave, and if it is true, like in this case, then sine wave is subtracted from the square wave. Thank you. Okay, alright, let us move ahead. Switch to the block diagram and now select a channel case. Alright. Now in this select a channel case is shown in this figure. Make these settings is shown here and then test the results. Alright. Take a build array function take the data of sine wave and square wave, and then you pick up an index array. An index array basically returns the element or subarray of n-dimensional array at index as you studied in previous lesson. Now in this case, user will have this option to select a channel. Either user wants row 0 or row 1. Row 0 is sine waveform and row 1 is square waveform. The user can select channel 0 or channel 1, and this is enum, and you also know how to create an enum. Alright. Connect the output to this waveform graph and also see it on this array, and also check the size of the array by using array size function. So array size should give you size of the array. Alright. Alright, so basically as discussed that this build array combines the sine and square waves into one 2D array, and then this index array basically extracts row 0 or row 1 from 2D array. The output from this function is a 1D array and is the waveform you select from with the select channel control. The select channel control. The waveform is displayed on the single channel of data waveform graph here, and the single channel of data array indicator here, and the select channel is basically a wire to row input of the index array function, and this array size is basically because you are using a 1D array, this function outputs a scalar value and shows you the size of the array. Alright. Please note that this is a select terminal function, and as per this condition, if you have selected channel 0 and if it is true, then the color of the channel 0 means sine wave, the color of sine wave will be blue, and if it is not channel 0, then it will be certainly channel 1 and the color of square wave will be red. And how it is done? This property node is used to change the color of the graph plot. You will learn about this property node in LabVIEW code 2. Alright. Now I hope you understood this portion of the code, and let us move to front panel and run the VI. You see channel 0 and color is blue and you get a sine wave. This channel 1, the color is red and it is a square wave. So this is how, with the help of index array, you can select a channel, either row 0 or row 1 using index array, and then see it on the waveform graph and as well as on 1D array. And the size of array is 1000 elements because it extracts 1000 elements from sine wave as well as square wave. Alright, stop the VI and go to the block diagram, and then complete the waveform data case. In waveform data case, this is the waveform data case. Alright. In waveform data case, select a build array. Take a build array. And then you should now use this direct waveform data type in this portion of the code in waveform data type in waveform data. Now as discussed, this waveform data type is a special kind of a cluster that contains additional timing information about the waveform. Like express VI generate dynamic data type. This function sine waveform generates basically a waveform data type, and this waveform data type contains additional timing information about the waveform as well. Let us use this waveform data type coming from this function and give it to build array. This waveform component only takes this waveform component from this function. But now we are using also timing information as well, therefore I have selected from here. Alright. Okay. Take one add function and connect it with the waveform data type coming of the square wave, and then add the offset. This is basically offset added into this square waveform, and then give it to build array, and then see the result on waveform data type graph. Now this is also a graph, waveform graph, but it contains additional information, timing information. As in previous case, when we were using simulate signal express VI, it also consisted of timing information, and this also consists of timing information as well. So now after this, you should know one thing. Please note one thing, that polymorphism is ability of VIs and functions to automatically adapt to accept input data at different data types, including arrays, scalars, and waveforms. VIs and functions are polymorphic to varying degrees. Alright, now switch to the front panel and test the waveform data case. This waveform data case. On the front panel, click the waveform data type and then run the VI. Now you see the offset is 0, therefore this square wave has offset of 0. Change the value of offset control and notice the square wave move on the waveform data chart. You see it moves on the waveform data chart. Alright. Okay, one thing more, you see this waveform data type also consists of timing information up to 1 second. Whereas you see here, when we were extracting only waveform component, not using waveform data type, then it does not consist of timing information. There is no timing information in this case, in select channel case. See here, because you are using basically only waveform component, this orange one. Now you are using basically this waveform data type, therefore you are getting also timing information about the waveform as well. So as the offset is added to square wave, so you can move the square wave up and down. This is the concept of offset, as you know. Alright. Stop the VI and then switch to the block diagram and go to all data channel default case and complete the block diagram as shown here. Alright, let us do this. Complete the block diagram. Pick one build array function alright, and take this sine wave data coming from here and then like previously add the offset. Up to now the code is same as our previous case. Alright, this is build array. Okay. Then show this on the waveform graph, all data channel waveform graph. Alright. Now let us do the same thing in another way by taking the for loop. Pick up a for loop. Alright. Pick up this waveform component of square wave and then perform the offsets, addition of offset like previously. You see it's a for loop and default behavior is that auto indexing is enabled. And then add the same offset here. Drag this build array, copy this component and give it to second component, and the first component is basically the same sine waveform component. So here in result you will get same data as you are getting, same signals as you are getting in this channel, all data channel. Let us copy it and verify this action, this behavior. Now on these both graphs you will get the same signals without any difference. Why? Because similarly you have taken the data points from this square wave and auto indexing is enabled, and then you have performed offset on this square wave function, and then again you have used the build array to make 2D array from this 1D array of a sine wave and another 1D array of square wave, and then you see it on this waveform graph. So these both waveform graphs should show the similar behavior. Also you can see this result on this 2D array as well. So connect it this 2D array to see the output as well on here. Alright. Okay. So simply add function modify the same data in one array by adding the value of the channel 1 offset to each element of the array. For loop basically extracts each element of the array using auto indexing so that add function in the for loop can add the scalar value. Build array takes the two 1D arrays and builds 2D array. Each 1D array becomes a row in the 2D array. Array size basically outputs 1D array, and you can use this array size as well. And this should basically now output you are checking array size of this 2D array, and it should show you basically 1D array where each element shows the size of each dimension. Like in this exercise, you have two elements of data for the number of rows and columns. So you will see number of rows and columns here. Okay. And these both waveform graphs and third this data channel array indicator should display the same data. So let us verify this. Okay. And let us run it. You see both graphs give you same data. And this is the same data that is also shown on this 2D array indicator. Alright. Change the value of channel 1 offset control to observe the behavior. See the behavior. You see this array which is of square wave information changes, and both graphs show the similar behavior. Same behavior. Alright. Okay, stop the VI and then move to the block diagram to complete the last case of waveform subset. Okay. Complete the waveform subset is shown in this figure 5.8. We are using one build array function and getting this one 2D array. And then we are using array subset function. You see, array subset returns a portion of array starting at index and containing length elements. You have already studied this function. So now we want to return a subarray, basically a portion of array from this basically 2D array. Therefore, we have used this array subset function. Alright. So it should start from index 0 and we are interested to see both of the rows, sine wave and square wave. Therefore, I select the length 2. Alright. So these constants specify that function extract the first two rows starting at element 0. Now this start value sets the start index. The default value is set to 0 at element 0. Alright. And finally, this length sets the number of elements to extract, how many elements you want to extract from these first two rows. You will define here. The default value is set to 1000. Now see this on waveform graph and as well as on this 2D array. Alright. Switch to the front panel and test the waveform subset case. Run it. Now you see you are getting from start value 0 to 1000 data points. Let us change the data points and you want to see, let us say you want to take 800 points from these two first rows. So you see now you get almost 800 points. Similarly, you can change the length, or you can select a subarray, a selected portion of the array from the main 2D array using this array subset function. This is waveform subset case. And you can also start, let us say you want to start collecting data points from 200 up to 800. So now in this case, it will start taking the data point from 200 and onwards and will take length up to 800. If you further increase this, you see you are taking less number of samples in this case because the start value is increased. And this is the default behavior where you are taking complete 1000 points starting from 0 with length of 1000. Alright, stop the VI and here we have completed this exercise 5.1 and we have used different array functions, manipulated array functions in this lab. Thank you very much. We will continue in our part 5 of lesson 5 in next video.